Hey everyone, good to see you again. I hope your quiz went well and it wasn't too crazy. I tried to make it easy as possible, but like I said, just wanted to make sure you were doing what you were supposed to be doing. I'm going to go over the practice problems I gave you on page 309, 6 and 7, and then we're going to look at fluids in motion and forces within liquids, and then evaporation and condensation quickly, and then I'll get you to do section 13.1 review for the rest of the class time. And yeah, that should conclude today's. And we will, sorry, those are also my roommates. Then we'll move to the solid state, the 13.2 for, sorry, I'm getting my days confused, for Thursday. Okay, awesome. So let's look at, sorry, let me get my life together. Sorry, I have a hurt foot and I'm supposed to run this race, so I have to wear this boot. Okay. Okay, so a girl is floating in a freshwater lake with her head just above the water. If she weighs 600 newtons, what is the volume of the submerged part of her body? Okay, so we know that our Fg equals the buoyant force, right? So F buoyant. Okay, and the buoyant force is equal to the density, in this case the density of water, times the volume, times G. Okay, so we're looking for the volume now, so all we have to do is rearrange the equation, and we'll get V equals Fg over density of water times G. Okay, so if you plug that in, your F of G, remember that's the mass, so 600 newtons. All right, taking it out of scientific notation, the density is 1,000 kilograms per meters cubed times G, which is 9.8. Okay, and when you do that, you get 0.06 meters cubed. All right, and this is the volume. This does not include the girl's head that is outside of the water, okay? But let me show you. All right. It's pretty simple, just rearranging the equation. All right. Do number 7. All right. Number 7 says, what is the tension in a wire supporting a 1250 Newton camera submerged in water? The volume of the camera is 8.3 times 10 to the negative 2 meters cubed. Okay. So to do that, we have the tension force plus the buoyant force is going to equal Fg, where Fg is the air weight of the camera. So it's the weight of the camera, okay? So then it says, what's the tension? So we're looking for that. So let's rearrange it to Ft equals Fg minus force buoyant. Okay, and when you do that, you have Fg 1,250 newtons. It tells you that in the problem. 1,250 newtons minus the buoyant force. So that's really going to be the density of water. So we'll do 1,000 like we did before. All right, times the volume of the camera, which is 8.3 times 10 to the negative 2, or you could do like 0.083 times 9.8, which is our G, right? And when you do that, you get 4.4 times 10 to the second newtons. Okay, it's in newtons. Why? Because we're looking for the tension force. Force is always in newtons. Okay, great. Hope those make sense to you. Now, the rest of the video is going to be a little bit boring, sorry. Also, sorry for the mess. We're moving everything because I'll be home in a few weeks. But yeah, so I don't mind this. The rest of this is going to be a little bit boring because I'm just going to be talking to you about a few different things. And then I'll just get you to do the 13.1 review, like I said. So just bear with me for the next like 10 or so minutes, and then I'll let you guys do some of those critical thinking problems that I think will really help you as you go further in your studies of physics, okay? All right, so let's look at fluids in motion. To see the effect of moving fluids, you could look at the experiment in 13.8. So hold a strip of notebook paper. You could actually do this, okay? So hold a strip of notebook paper just under your lower lip, and if you blow hard across the top surface, the strip of paper will rise. So this is because the pressure on the top of the paper, where air is flowing rapidly, is lower than the pressure beneath it, where the air is not going to be in motion, all right? So take a second to try that if you want to. The relationship between the velocity and pressure exerted on a moving fluid it will be Bernoulli's principle, okay? So named for the Swiss scientist Daniel Bernoulli. It states that as the velocity of a fluid increases, the pressure exerted by that fluid decreases. So velocity increases, pressure decreases, okay? So also if velocity decreases, then pressure increases, right? It has that inverse relationship, okay? So when a fluid flows through a constriction, its velocity increases. So you may have seen this happen as the water flow in a stream speeds up as it passes through like the more narrow sections. Consider a horizontal pipe completely filled with a smoothly flowing ideal fluid. If a certain mass of the fluid enters one end of the pipe, then an equal mass must come out of the other end, right? So if you insert a certain mass of something, then it should come out, the same mass should come out of the end, right? So consider a section of the pipe with a cross section that becomes narrower. If you look at 13.9, it kind of gives you an example of that right there. You can see how P2 and B2, the narrow part, goes right there. Okay, so to keep the same mass of fluid moving through a narrow section in a fixed amount of time, the fluid moving through the narrow section in a fixed amount of time, the velocity of the fluid has to increase. So because it has a narrow area, so it needs to be quicker to get through because less is coming through at one particular time, if that makes any sense. Okay, so if the velocity increases, so does the kinetic energy, right? Because it's going faster, and kinetic energy is the energy of motion. So this means that the net work must be done on the fluid. So the work is proportional to the force on the fluid, which in turn depends on the pressure. If the net work is positive, then the pressure at the input end of the section where the velocity is lower must be larger than the pressure at the output end where the velocity is going to be higher. So most aircraft get part of their lift by taking advantage of Bernoulli's principle. So airplane wings are airfoils, so devices that are designed to produce and lift, like when moving through a fluid. So like the curvature of the top of the wing is greater than that of the bottom. So as the wing travels through the air moving over the top of the surface travels further and therefore must go faster than the air moving past the bottom surface. Okay, so that's just a real-world example of how Bernoulli's principle is used in everyday life, right? So the decreased air pressure created on the top of the surface results in a net upward pressure that produces an upward force on the wings, or it causes them to lift, is basically what they're saying. So it helps to hold the airplane up. Let's look at streamlines. So automobile and aircraft manufacturers spend a great deal of time and money testing new designs and wind tunnels to ensure the greatest efficiency of movement through air, which is actually a fluid. Okay, so this is how the movement of liquids and all of this fits into it, okay? So the flow of fluids around objects is represented by streamlines. If you look at figure 13.10, you can see that there. The smooth streamlines shown in this computer simulation indicates smooth airflow around a jet fighter. So that's what you're looking at there. So streamlines can best be illustrated by a simple demonstration. Imagine carefully squeezing tiny drops of food coloring into a smooth flowing liquid. If the color lines that form stay thin and well defined, the flow is said to be streamlined. So that's just, I mean, that's another kind of experiment that you could do if you wanted to. So notice that if the flow narrows, the streamlines move even closer. So closely spaced streamlines indicate greater velocity, and therefore, due to Bernoulli's principle, it would have a reduced pressure, right? If streamlines swirl and become diffused, the flow of the fluid is said to be turbulent. So Bernoulli's principle does not apply to the turbulent flow, okay? Sorry, my foot hurts so bad. Okay. So, forces that are in liquids. Let's look at that. This is on 310 if you're a little bit lost. So the liquids considered so far have been, like we talked about it at the beginning of the chapter, these have all been ideal liquids in which the particles are totally free to slide over and around one another. In real fluids, however, particles exert electromagnetic forces of attraction on each other. These are called cohesive forces, okay? And they affect the behavior of the liquid. So if you look at surface tension, have you ever noticed that the dewdrops on spider webs and falling drops of oil are nearly spherical? So what happens when it rains just after you've washed or waxed your car? The water drops will beat up into rounded shapes. If you look at 1311, you can kind of see that there. So all of these phenomena are examples of surface tension, and surface tension is a result of the cohesive forces among the particles of a liquid. So it's the tendency of the surface of a liquid to contract into the smallest possible area. So that's what those water droplets are doing. So if you So if you notice that beneath the surface of the liquid, if you look in 1312, each particle of the liquid is attracted equally in all directions by neighboring particles, and even to the particles of the wall of the container. So as a result, no net force acts on any of the particles beneath the surface, okay? At the surface, however, the particles are attracted downward to the sides, but not upward. There's a net downward force, which acts on the top layers and causes the surface layer to be slightly compressed. So why does surface tension produce spherical drops, though? So the force pulling the surface particles into the liquid causes the surface to become as small as possible, as I just said previously. So the shape that has the least surface for a given volume is a sphere. So that's why it's that way. So the higher surface tension of the liquid, the more resistant the liquid is to having its surface broken. Liquid mercury has much stronger cohesive forces among its particle than water does. Remember that. That could be a possible question on your test. But if you look at some other liquids like alcohol and ether, they have weaker cohesive forces among their particles. A drop of either of like these liquids, they would flatten out onto the surface, okay? It's because it doesn't have a strong cohesive force. Let's look at capillary action. So you have cohesion, and then you have a force that's similar to that, which is adhesion. Okay, it's the attractive force that acts between particles of different substances. So it's kind of similar to cohesive forces. Adhesive forces they're electromagnetic in nature, just like I said, just like the cohesive forces. So if a piece of glass tubing with a small inner diameter is placed in water, the water rises inside the tube. The water rises because the adhesive forces between glass and water molecules are stronger than the cohesive forces between water molecules. So this is called capillary action. The water continues to rise until the weight of the water lifted balance the total adhesive forces between the glass and water molecules. So with cohesion, it's within the water, and then if it's adhesion, it's like between different substances. So this is the glass and the water. So that's kind of what you need to know with that. Let's look at evaporation and condensation on 312, and that'll finish up our section today. And yeah, we'll do you'll do 13.1, and I will go over that for you tomorrow. Like I said, I will be traveling, but I'll be able to get it to you tomorrow for Thursday. Okay. So evaporation and condensation. What happens when you have a puddle of water on like a super hot day? So after a few hours, you notice that the water is gone, right? The water dries up. So why? The particles in the liquid move at a random speed. So the temperature of a liquid is dependent on the average kinetic energy of its particles. So the movement, right? Some are moving rapidly, others are moving more slow. So suppose a fast-moving particle is near the surface of the liquid. If it can break through the surface layers, it will escape from the liquid. Because there's a net downward cohesive force at the surface, only the more energetic particles can escape. So the escape of these particles, that's what evaporation is, basically, in like scientific terms. That's what evaporation is. So it has a cooling effect. So like on a hot day, our body sweats, right? The evaporation of your sweat cools you down. In a puddle of water, evaporation causes the remaining liquid to cool down. Each time a particle with higher than average kinetic energy escapes from the liquid, the average kinetic energy of the remaining particles will decrease, okay? And a decrease in the kinetic energy is a decrease, therefore, in the temperature, right? So when it's moving quicker, the temperature rises. When it moves slower, the temperature decreases, right? So you can test this cooling effect by pouring a little rubbing alcohol into the palm of your hand. So like alcohol molecules evaporate easily because they have weak cohesive forces, like we talked about just a second ago, okay? The cooling effect is really noticeable, though. A liquid that evaporates quickly is called a volatile liquid, okay? So make sure you know that. So let's look at particles of liquid that have evaporated into the air can also return back to the liquid phase if the kinetic energy or temperature decreases in a process called condensation. So what happens if you bring a cold glass into a hot, humid area? The outside of the glass, it'll become coated, right? It'll start to sweat, kind of, into a hot, it becomes coated with condensed water. Water molecules moving randomly in the air surrounding the glass strike the cold surface, and if they lose enough energy, the cohesive forces become strong enough to prevent them to escape. So you'll have that condensation on your glass. So the air above any body of water contains evaporated water vapor, which is water in the form of gas. If you look at 13:14. If the temperature is reduced, the water vapor condenses around tiny dust particles in the air, producing droplets only 0.01 millimeters in diameter. So a cloud of these droplets is called fog. Fog often forms when moist air is chilled by the cold ground. So it can also be formed in your home, which I don't know if a lot of people know. When a carbonated drink is opened, the sudden decrease in the pressure causes the temperature of the liquid to drop, which condenses the surrounding water vapor. Okay, this is all stuff that I feel like you kind of have known already, but this just puts it more in the physics terms. Yeah, so we're about 20 minutes right now. You've got about 25 minutes left. So that'll give you some time to do on 313, 13.1 section review that deals more with the critical thinking. Yeah. So this will be for, trying to think of the days. Okay, so this is Wednesday. Yeah, I heard that at least the girls, I don't know about the boys. I didn't hear anything about the boys having their, they have another game on Thursday. So I just let you know, I'll be thinking about you ladies. I did the same thing this time 10 years ago. I was a pitcher too, Sarah. So, yeah, so I'm just thinking about you ladies, and the boys too, and your coaches and everyone who will be with you or have a part in your playoff experience. So yes, go baseball and softball, and I will hear from my sister how you both teams did. But yeah, go Rebels, and I will talk to you all tomorrow. Bye.